Leave a hot cup of coffee in a cold room, and it slowly loses its heat to the surrounding air. The coffee cools down. Release a pressurized cloud of cooking gas into an empty space, and it rapidly expands outward to fill the entire container. You will never see that gas spontaneously compress itself back into a tight sphere in the corner. Stirring a thick bowl of soup transfers your kinetic energy into the liquid, warming it up, but heating a bowl of soup will never cause the spoon to start spinning on its own. Here we run into a strange paradox. The mathematical equations of basic mechanics work perfectly well in reverse. If you track a planet orbiting a star, the math allows the planet to run backward along that exact same path. But everyday thermodynamic events do not work this way. These macroscopic natural processes have a strict, irreversible direction. They act as a one-way street for energy in the universe. To perfectly reverse a physical process, you have to meet a punishing requirement. You must return both the system itself and the entire surrounding universe exactly to their initial starting conditions. Take that expanding gas. When a partition is removed, particles rush chaotically into the empty space, passing through non-equilibrium states. The pressure and temperature lack uniform values. The same breakdown occurs during an explosive chemical reaction, with sudden localized pockets of extreme heat and pressure spikes. The variables are so erratic, there is no coherent mathematical pathway back to the start. The speed and chaos of these events destroy the roadmap back to the start. The action leaves permanent, unerasable changes in the environment. Physicists wanted to study reversibility anyway, so they created a highly sanitized imaginary laboratory condition, a theoretical workaround to make perfectly reversible actions possible. They rely on what is called a quasi-static process. A quasi-static process is a physical change that occurs infinitely slowly. Imagine compressing a gas by pushing a piston down in microscopic, infinitely slow increments. Because the movement is so slow, the gas has time to adjust its pressure and temperature uniformly. It remains in perfect thermal and mechanical equilibrium at every single stage. Look closely at the variables here. At any given moment, the internal pressure and temperature of the gas differ from the outside environment by only an infinitesimal amount. You completely avoid the chaotic gradients that happen during rapid expansion. Because the system stays perfectly balanced from start to finish, you know the exact values needed to push it backward. This infinitely slow progression is the only mathematical way a process can occur without leaving a permanent trace. But we do not build infinitely slow, ideal pistons. Look at the massive, high-speed reality of human engineering in this photograph of a locomotive. A machine that operates infinitely slowly produces zero useful power for the real world. You cannot run a transportation network on a quasi-static process. The moment you accelerate a piston to a practical speed, the gas inside doesn't have time to equalize. You instantly introduce internal turbulence and severe temperature imbalances. Those rapid, violent changes push the gas immediately back into a non-equilibrium state. The reversible chain is broken. The very act of making a machine fast enough to be useful guarantees that its operation can never be perfectly reversed. What specific physical forces are actively stealing a system's ability to run backward? The primary culprits are dissipative effects, chiefly mechanical friction. Even the smoothest piston has jagged atomic ridges catching against the cylinder wall. This friction converts organized mechanical work into random thermal energy. That heat dissipates into the surroundings, permanently lost. Another major factor is viscosity. Viscosity is the internal friction of fluid layers. It's the resistance a fluid has to smooth, reversible flow. When you stir a liquid, those internal layers grind against each other. Viscosity ensures that the kinetic energy of your spoon is permanently scattered as heat throughout the fluid. These dissipative effects act as a universal thermodynamic tax. Every real action you take permanently loses some energy to the environment. True reversible processes are a physical myth. They exist only on chalkboards as mathematical benchmarks. Physicists use this impossible standard to calculate the absolute maximum theoretical efficiency a machine could possibly achieve before the real world gets in the way. Fighting friction, minimizing viscosity, and struggling against chaotic, non-equilibrium states is the ultimate, unwinnable boundary of all modern engineering. This inherent irreversibility explains why shattered glass doesn't spontaneously reassemble, and why the steam from your coffee won't crawl back into the cup. It is the fundamental reason why the universe and time itself only moves forward.